Michael Möller is a full professor for computer vision and the head of the group for visual scene analysis at University of Siegen. He obtained his doctoral degree 2012 from the University of Münster and in collaboration with University of California, Los Angeles, where he spent 2 years as a visiting researcher. After his PhD, he worked at Arnold and Richter before joining the computer vision group of Professor Daniel Kremers at TU Munich as postdoctoral researcher. Michael is well known for his work on convex optimization, variational methods, compressed sensing, and multiscale methods with application in image processing and computer vision. Michael received many awards, among them Best Paper Honorable Mention at CVPR 2016 for his work on sublabel accurate relaxations of non-convex energies. And without further ado, we're looking forward to your talk.
Wow, thank you so much for putting up this nice workshop, inviting me, and then even having this very kind introduction. Thanks a lot. So I hope my screen is visible now. And yes, maybe I can try to minimize occlusions here. All right, perfect. So welcome everyone. Thanks for showing interest in this topic. Basically, my first slide, where I wanted to motivate why it might be interesting to learn more on quantum computing, has been nicely covered in even more detail by Tolga already. So I wanted to show you that many problems from computer vision now go into the direction of quantum computing, and it's still a very early area with lots of things to explore and to do. But I think in the interest of time, I'll just skip this because this was so nicely introduced by Tolga already, and go to the main point of my talk already. I really want to start from scratch here as being the first speaker. And assuming many of you don't have a background in quantum computing, I thought I'd start, well, where I started 3 or 4 years ago, at basically zero knowledge about quantum computing. And the way I want to do this is introduce 4 basic assumptions that you kind of need to believe that physicists have found out. And once you accepted these things from the physical world, show you how a specific type of quantum computing called quantum annealing can be used to solve specific optimization problems that are of large interest in computer vision. And this, why you can solve these problems, is then a consequence of math and not of some miraculous quantum thing that you need to believe. And at least this helped me to get into this world. So I'm requiring no physical knowledge, just some acceptance of some mathematical properties our world at a tiny scale seems to have. All right, so, and also feel free to interrupt me anytime. So this is really supposed to be an introductory talk with possible discussions as well. So the first thing you are probably familiar with in a classical computer, the smallest piece of information we represent is a bit, and a bit can have 2 values, 0 or 1. And this is the first part already where a quantum computer would differ, namely quantum bits, or short qubits, would be mathematically rather a vector of length 2, a complex vector of length 2, where I am adapting the notation that physicists often used, called cat notation here. So this, don't be irritated by this bar and this bracket. So this is just a vector in C2, and these qubits are described by vectors of length 1. And now why are they described like this? Because one found out that they can behave a little weirdly, namely they can not only be in either one state or the other, but they can also kind of be in both at the same time, meaning mathematically, you represent your vector of length 2 as a linear combination in an orthonormal basis here. So this is why I've written alpha 0. So this 0 here just stands for one basis vector that we could call or identify with the state being 0, and plus beta 1 here. So this 0 and 1 are also vectors in C2. and are normalized and orthogonal. And then it turns out that measuring the state of this qubit in this computational basis gives 0 with a certain probability, namely the absolute value of the coefficient squared, and 1 with the corresponding probability of the corresponding coefficient in absolute value squared. And since this qubit is normalized here, of course, a squared plus b squared is equal to 1. So in this sense, it all makes sense. The only thing that maybe at first does not make sense, that we have really a fundamental stochasticity in here. So usually when you think about random events like playing roulette or so, then this randomness just comes from you being unable to determine the exact state the turning roulette wheel and the ball you throw in there comes from. But here it seems to be very fundamental that it's real randomness here. And this you might have heard in popular science talks, illustrated, for instance, by Schrödinger's cat. So if you would be able to fully isolate a quantum system where you have a radioactive particle that can indeed be described basically by what I have shown you, namely something that is at the same time decayed and not decayed with some probability, then this paradox says the cat, which is now in this box and connected to some poisonous gas, being smashed if the radioactive atom decayed, and, well, not being smashed if the atom did not decay, would also be alive and dead at the same time. And now the fundamental thing in quantum physics is once you measure, the state gets fixed. So it collapses into either 0 or 1. So the cat would be alive and dead at the same time up to the point where you measure, and then it's decided what happened here. So indeed, the world is weird at this scale. And it gets even weirder when we think about what happens if we consider more than one qubit. Okay, and I'll take the math approach. I'll do 1, 2, and then n. So what happens if we have 2 qubits? So I have some function psi here that I represent in a linear combination in my orthonormal basis. I have another function phi here, which I represent with different coefficients in the same basis. And now it's quite natural to think, well, how would I describe this? What can happen is, well, the thing I just showed you in assumption 2 happens for each of the 2 qubits separately. So if I measure psi, I get 0 with probability value alpha squared, 1 with probability value beta squared, and similarly for phi with gamma and delta squared. And so if you think about these 2 qubits being separated from one another, it's quite clear that you would think, well, if I measure both qubits, I will get 0 and 0 with probability, well, product of alpha squared and gamma squared. And I'm getting 0 and 1 with probability alpha squared and delta squared. And I'm getting 1 and 0 and 1 and 1 with the product of the 2 probabilities, which always happens if you have 2 statistically independent events, right? This is throw the dice twice, you multiply the probability of the possible outcomes. Okay. This means, okay, there arises the product of all my coefficients squared. So it's quite natural to say, if I have 2 qubits, let's represent the system by taking the tensor product of the 2 representations. Because in the tensor product, you take all products of all components. So you essentially expose these products with the corresponding states in a single description. So it would be alpha gamma times 0, 0, alpha delta times 0, 1, and so on. Okay, because then this property is preserved that you measure the state we see here in this basis with the probability of the coefficient squared. Yeah? Very good. And if we think about this, maybe for a second, I'll leave out these weird 0 tensor 0, 0 tensor 1 or so things, and I'm just focusing on the coefficients we have here, and I write them into a matrix. So essentially, my state of 2 qubits can be represented or explained by the 4 coefficients alpha, gamma, beta, gamma, alpha, delta, beta, delta, corresponding to being in state 0, 0, 0, 1, 1, 0, and 1, 1. And it's not hard to see that this matrix is the outer product of two vectors, or the tensor product. I mean, this is how we constructed this whole thing. It's the vector alpha beta times the vector gamma delta. So I described this state of qubits, these two qubits, by a 2 by 2 matrix, but I've shown you that this matrix is always of rank 1. Right? It's a vector times a vector, an outer product. We all agree that's a rank 1 matrix. And I have made no assumptions on these qubits, so it will always be rank 1. Right? So our expectation would be, if I have two qubits, then, okay, it's convenient for me to describe it in this 4-dimensional space of 2 by 2 matrices, but true systems can only occupy a small set within these 2 by 2 matrices, namely those matrices that are of rank 1. And now comes the shocking part. This is wrong. Physicists found out that you can occupy the entire space. You can go to any 2 by 2 matrix. It does not need to be rank 1. So indeed, for now talking about n qubits, you would take the outer product or the tensor product of n many vectors of length 2. So you would end up with a space of size 2 to the power of n. Your entries would be norm 1, and you would think your n qubits can only occupy a tiny portion of the space, but it turns out they can occupy anything, and this property is called entanglement. Or Einstein called this a spooky action at a distance. Why is it spooky? Because it now means that the probability of measuring something in one qubit is not independent of the probability of the other qubit being in a certain state anymore. And what indeed people have done, and what they received even experimentally a Nobel Prize for, is prepare two qubits, then in such a way that they are entangled, then take one qubit, carry it to another place, and this is how you carry a qubit. Then you measure what this qubit does, in which state it is, and what you measure here instantaneously fixes the state of the other qubit. And this is why Einstein called it a spooky action at a distance, because it doesn't, like other effects, need some time to get to this other qubit, but it really happens instantaneously, no matter how far I walked with my qubit. All right, so this is again possibly weird, but important, because it means we can represent any vector in this space c to the power of 2 to the power of n with n many qubits. And now the only left assumption I need to tell you for you to understand how quantum computing, or this aspect of quantum computing that I want to talk about, namely quantum annealing, works, is understand how multiple qubits behave over time. And this is, don't be shocked by the slide now, known as Schrödinger's equation. So physicists have found how to describe how a system of qubits described by this vector psi here behaves over time. And it's this equation, so basically the imaginary number I times a factor times the time derivative of that qubit state is equal to some large matrix, so 2 to the power of n by 2 to the power of n matrix, times this state. All right. And at this point, you might be thinking, what does this have to do with fast computations for computer vision? And the reason is this is enough to develop a strategy for solving optimization problems of this form, being called quadratic unconstrained binary optimization problems, or QUBOs. So you can minimize over binary x transpose w x just based on these four assumptions. Why? All right, it is possible by physicists to prepare n qubits in an initial state that is the smallest eigenvector to one of these matrices H that appeared in the Schrödinger equation that we also call Hamiltonian. Then we can use interactions between these qubits, and not too many, so only n squared, many physical interactions between these qubits, to create another matrix, and even a very special one, namely a diagonal matrix, whose entries along the diagonal are the 2 to the power of n many values that we can get for x transpose w x. So if you think about how many values do we have, well, it's a vector x of length n, and each entry can have the value 0 or 1, so there are 2 to the power of n many, and we can arrange them in a diagonal on a 2 to the power of n times 2 to the power of n large matrix. Of course, we as computer scientists never want to build this matrix. This is impossible to fit in the computer. I mean, this is where the difficulty of the whole problem comes from. But it's possible to realize physically with only n qubits and n squared many interactions. And then there is really a theorem, and this is not something you have to believe, but that you could prove with pen and paper, that if we now start with this initial state and slowly take this operator, this Hamiltonian, to the Hamiltonian that is diagonal, then the system of qubits will remain in the state of lowest energy, so will be an eigenvector corresponding to the smallest eigenvalue of h for all times. Okay, that sounds now very mathematical, but it's not that insane, because if you think about what is the eigenvector to the smallest eigenvalue of a diagonal matrix, well, it's a vector that is 0 everywhere except one entry that is 1, and it's 1 exactly at that point where the number is lowest on your diagonal. Right, this is the eigenvalue, the corresponding one then. It's, well, eigenvectors of a diagonal matrix are not that exciting, but it means you can identify this eigenvector then, again with a solution to your optimization problem, because you know you'll get an eigenvector that corresponds to the minimum entry of x transpose wx. So it means if I take my Hamiltonian from some initial point to this diagonal one, and it all behaves according to the Schrödinger equation, then approximately, at least at the end of doing this, I can just measure my solution to the optimization problem. All right. So the principal idea is I can, maybe very big picture, I can do some physics such that I can ultimately measure the solution to a very complex optimization problem. Let's see how I'm doing on time, 15 minutes into the talk. Okay, yes. So maybe I can at least briefly tell you how that works to understand that this is really just a math consequence and not something weird. This differential equation, I know these things look nasty with the bars and so on, but it's not that complicated. It says the temporal derivative of a vector is equal to, basically, let's think of this as a factor, and the I and h as well. Temporal derivative of a vector is a factor times the vector itself. If the factor was a scalar factor, this is something you know how to solve. This is e to the power of t times that factor. Now things are a little more complicated because this factor is not a factor, but is a matrix. And this is the point where, in case you have seen differential equations before, it's very natural to try to do exactly the computation that I just told you, but after representing this thing, psi here, in the eigenbasis of this matrix we have. Because then it hopefully boils down to pretty much the equation I've just told you. And this is indeed almost true. So if we represent this psi here in some basis of eigenvectors of h of t for each time step t, then we get for the coefficients basically I times alpha prime is equal to something times alpha prime. So this thing that you can indeed solve and know how to solve. And this would be very nice. If this was true exactly, it would mean each coefficient behaves independently of all others. Right? It would mean if I initialize one coefficient at 1 and all others at 0, this will remain the same, will remain true over all times. This is just a consequence of this equation. This is not so hard. This is only true approximately, namely up to some error term. But if we ignore this error term for a second, then here really the solution would be, well, if I initialize with the state of lowest energy, then this equation immediately tells me I won't ever leave it. So we can measure the solution of a QUBO with quantum computing. Now, maybe the bad news, this is not quite true. And it would also be very surprising because classically QUBOs have been proven to be very difficult, NP hard. So that would mean we would have some sort of free lunch that physics can do this. So rather than this, I would like to tell you the I don't know how bad truth, but this error term I've been talking about can be specified in some way that again looks complicated, but ignore the sum and just see what it depends on. So the numerator here gets small if the changes in the matrix here, so the temporal derivative of h, is small. And how small should this be? It should be small in comparison to, and the denominator here is difference from the eigenvalues, lambda k, to the smallest eigenvalue. So considering that the most important thing is this lambda 2, it must be the changes in this operator here need to be small in comparison to what we call the spectral gap, namely the difference of the second smallest and the smallest eigenvalue of this matrix. All right, and now you can even start discussing computational complexity of this approach, quantum annealing. Namely, is it NP, in some sense, NP hard in the quantum world? This is now very inaccurate, but if we think about being NP hard as something like we expect exponential runtime in order to solve these problems, then, well, it's related to will this spectral gap here close so fast that this error term here, or sorry, the 1 over the spectral gap grows exponentially. If this grows exponentially, we have to compensate for this by making the transition, this temporal derivative of h smaller, ultimately meaning we will need exponentially increasing time to do our change of the system and measuring the solution to the optimization problem. And currently, it is not really believed that we can solve such NP-hard problems in polynomial time with quantum computing. Yet, at the current state, I would still say quantum annealing is a very exciting heuristic, and even if we get some acceleration out of this, so polynomial acceleration, it could make a huge difference. And maybe even one thing that is underestimated in the O of something complexity is the constant, right? If the constant is many, many years for problems we care about, then it could still be hurtful. And if the constant is 10 to the minus 9 seconds or so, it's a very nice constant to have for many, many problems. All right. So this would conclude the technical part, to give you a little background on how quantum annealing works. Second part is on applications. So where can we use this? And as an exemplary motivation, I picked out shape matching. And since you have suffered through some formulas, I thought I'd also throw in some nice pictures. So what is could be a motivation for doing shape matching? Well, it's the technique of finding correspondences between 3D shapes. and how this is currently done. For instance, in movie industry, you make the actor wear such suits in order to then know that this point, which you can then easily track by an active measurement, corresponds to the arm of the ape or to the arm of Gollum or so. If you think about doing this without special suits, then maybe the problem looks like this. We have some actor that is in some pose, and we have Gollum as a default model in our computer, and we want to identify that this arm point is this arm point and so on. No, this arm point and so on. So maybe doing it even more technically, it means you number the discrete representation of your geometry, and you have another discrete representation of your geometry, and you try to find correspondences that x1 corresponds to z2 semantically. Something that is not so hard for humans to see, but that is not so easy for a computer to figure out automatically, and where a common representation is what we call a permutation matrix. So basically a one-hot encoding of every match. So if this is x1, so 0.1 corresponds to 0.2, then the first row of my permutation matrix has a 1 in the second position. And similarly, x2 matches to z6, so the second row has a 1 in the sixth position. And this is particularly challenging because my situation was, of course, very simplified, so a more realistic version of the hat is not 1 point, but a couple of thousand points. All right, what is one way to tackle this problem? It's to assume the shapes deformed isometrically. Isometric means you're comparing geodesic distances. If you have not heard this term, how far does an ant have to walk if it's clever and takes the shortest path on the shape? How far is the way for this ant? And the idea is all the deformations, at least we as humans can do, are approximately isometric, so the distance of my hand to my elbow doesn't change if I do this. And this holds approximately for all distances we have. And so we would formulate classically a minimization problem that looks like this and basically says if point I on shape 1 gets mapped to point K on shape 2, and point J on shape 1 gets mapped to point L on shape 2, then the geodesic distance between I and J and K and L on one shape and the other should be similar. I hope this makes sense. Otherwise, you can also just accept these are some quadratic costs that arise from modeling this problem. And we are trying to solve this over permutation matrices, which are very special matrices, namely every entry is either 0 or 1, and you have 1, 1 per row and 1, 1 per column. So you have some linear constraints here. And now, one reason why math is great, you can now just define stuff to simplify the notation. So you say this sum over ij, k, l, and costs, well, you just write it as x transpose sum matrix W times x, because you know this is quadratic, it can be written this way, after vectorizing the matrix here. And you have some linear constraints, so linear constraints can always be written as ax equal to b. And then a nice result from optimization, well known, is for these binary problems, you can actually add any linear equality constraint by a quadratic penalty. All right. Now, this means after adding it to as a quadratic penalty, you ultimately arrive at a quadratic problem over binary variables. So exactly the form that in the first part I motivated, we can solve on a quantum computer. So, why am I not done here, and why was Tolga and I advertising that there is still a lot to be done? This might seem solved now. It's not. So what is our starting point? The nice thing is we are actually getting to the point where we can solve problems of practically relevant size on actual quantum hardware. So the largest commercially available quantum annealer comes from the company D-Wave. It's called Advantage. I think Advantage 2 is wrong, but I'll be corrected by this in in an hour or so. It has about 5,500 qubits, so this is a size where these QUBOs are already really difficult to solve classically, but there are still some remaining challenges. So one is it's difficult to keep these qubits physically stable for a long time, so to shield them from outer influences basically. So we cannot guarantee that our transition is slow enough in the sense of part one of the talk. Second, the spectral gap is almost impossible to compute for almost all problems because, well, it depends on eigenvectors of a matrix that is so large we cannot even set it up. And third problem is, or one way to at least deal with this is the default annealing time is quite short, so 20 microseconds. And then one typically does this many times, like 1,000 times or so, and then tries to get a statistic of which solutions you got, because this outer influence and noise is different every time you run it. Second is the weights cannot be fully arbitrary. So for instance, they need to be quantized to realize physical couplings in the computer. And cannot be arbitrary in the sense of not every qubit can naturally talk to any other qubit, meaning the natural matrix W would not be non-zero everywhere. We have a certain pattern that we need to respect. And one nice way to circumvent this pattern is to use more qubits on the quantum computer than logical qubits in your problem by introducing additional constraints. So instead of having 3 qubits, everyone talks to everyone, you duplicate 1 qubit, you make sure they are equal, and then by this you have gained basically 1 extra connection such that through this loop still every qubit can talk to every other qubit, provided that you make sure these two remain the same during the whole time. All right. With these difficulties, at first we were kind of surprised how difficult it is. So our first naive approach, where, okay, the contribution lied a little differently, namely how to incorporate these equality constraints in different manners. This is why you see multiple crosses and X's here. I'm showing you here for 10 different instances of matching 4 points to 4 other points. How likely was the quantum annealer to give us the right solution? And, well, 4 points to 4 points, number of permutations is 4 faculties, so 24 options. Random guessing, 1/24 is like a little lower than 5% success chance by random guessing. Annealing was around that limit. So not much better than random guessing if you don't find a smarter way of tackling this problem. And luckily, we were able to find smarter ways, namely, in order to avoid having to constrain our problem, we rather want to iteratively move within the set of permutation matrices, basically asking always, do we want to permute these two or leave them as they are for a couple of candidates? And this makes sure we can avoid incorporating these permutation constraints. And this allowed us to go up to reasonable sizes, so matching 512 points to 512 points, as good as basically classical methods have been 10 years ago. And now the nice thing for this year's CVPR is by extending such an approach to multiple shapes, we are now able to match the state-of-the-art classically on reasonable resolution sizes, and we'll have a poster on this in the poster session as well as in the main conference. So, to sum up, take-home message would be, I think quantum annealing is a very exciting meta-heuristic for solving quadratic unconstrained binary optimization problems. The current hardware is starting to become usable at very relevant scale for computer vision problems. Annealing time, quantization, constraints, and connectivity are still major challenges that certainly motivate additional algorithms such that hybrid methods that can cope with such limitations. And for me, it's just very exciting to consider what happens if we can solve quadratic binary optimization problems fast and to high quality now. So this is kind of the application-driven motivation. And with this, I would like to thank you for your attention and do 1 minute of advertisement. So in Siegen, we're just establishing more research and a study program in this direction, including a master on quantum science. I'm happy to offer scholarships for PhD visits, so please ping me and my email address in case you're interested. And there's even some co-hardware development. So we have a startup in Siegen working on building quantum computers such that my limited knowledge about the hardware can be compensated from people in physics. Thanks a lot.
Thank you very much for this exciting talk, and we have time for questions. If you have a question, please come to the microphone in the middle of the room.
Shocked everyone. No, not everyone.
Thanks. That was a really engaging talk. When folks are doing research on quantum computers, where are they going? I assume not everybody has one of these in their house.
Yes, so we are accessing the D-Wave machine remotely, so they offer this as a commercial product. I think you can try it out with like 1 minute of free computing time. Looking in this direction, yes. And this is this one architecture of an annealer. To be fair, there are also other architectures of quantum computing. So talking about quantum machine learning, we'll probably also hear about gate-based quantum computing, where there are also a couple of machines much smaller at scale, a couple of qubits. IBM, for instance, has this offer to access their machine for a different type of computation that I showed. And of course, partially we simulate because we cannot run everything on a quantum computer. Yes?
Yeah, I'm just wondering, it's very interesting, but how close are we to actually applying this? You know, like if I'm an engineer, like thinking about learning Q-sharp and that kind of things, do you think it will be useful in industry in like the next 5 to 10 years?
That is a good but also a difficult question. So I would hope yes. On the side of hybrid solvers, I'm much more confident. Whether really what I pitched at the very beginning, so a pure quantum solution, is already good enough. For some problems, maybe yes. With these constraints, you certainly need some extra idea on how to deal with them.
Okay, but can you run like a qubit machine? You can actually solve some real-world problems?
I mean, what I showed here, these and these were run on an actual quantum computer generating these results. So in this sense, yes.
Thanks for the talk. So one question I had was that with GPUs, what's really caused the big revolution is being able to do a bunch of matrix vector multiplications, you know, really repeatedly and fast. And here you talked about the interaction of quantum computing with CPU. Is there also like interaction of QPUs and GPUs that like can kind of feed off each other in different ways? So from the cubo solves there and the linear algebra on the GPU side?
Excellent question. Yes. Yes. So indeed, when developing hybrid approaches, I think we natively use the classical device that was most suited. It's not that the GPU directly talks to the quantum computer, so it still goes back through regular memory, and then because we send it online basically. But yes, it could be thinkable to really use the best of all computational capabilities you have available today. Yeah, very good. Thanks.
Any other questions? Yes, please.
Thank you for the talk. So in addition to, I wanted to ask about like applications of this direction. In addition to efficiency-based applications, are there any, like, do you foresee it being applied to things like, I don't know, like quantum consciousness or something that is more geared toward like AI, making machines more sentient and stuff?
Ooh, I know too little about this field to dare to answer. So the very technical response for me would be anything that you phrase as a combinatorial optimization problem has a good chance of being relevant here. Whether I can phrase the AI consciousness as such, I know too little about to say. Sorry.
Thank you.
Thanks a lot. I was wondering if you know much about the field of quantum photonics, and I was just wondering if the choice of let's say, modality for quantum computation affects algorithm design. Like, how is what you would do for D-Wave different than what you would do with a quantum photonics computer, for example?
Yes. So for sure, some of these limitations that I mentioned are different for different hardware. So for instance, how many qubits and in what way qubits can talk to one another is even different for different realizations of D-Wave. And also how stable these things are, so how long can I make the annealing time and so on. This differs from machine to machine, and therefore if you develop hybrid approaches that try to take the best out of your current quantum machine, that could indeed be completely different for different hardware.
Okay, thank you.
Thanks.
All right, maybe time for one more last question. Yes, please.
Thank you for the talk. I just want to know if you've, like this quantum annealing, first, how does it compare to simulated annealing and the classical optimization? And also, is it applicable to other types of optimization that we would love to have in like deep learning, hyperparameter optimizations, hyperparameter search type of things, or just general comments?
Yeah. So currently we are indeed using simulated annealing sometimes to illustrate our approaches, but on the long run we would of course hope that quantum annealing does significantly better. This would be the motivation for doing all this, of course. And regarding your second question, a limitation currently is we have to find costs that are quadratic, or possibly in the future polynomial. Hyperparameter optimization in machine learning in a deep network, very difficult to formulate as a quadratic problem. Of course, you can use Taylor's expansion and then iterate or so, but how close that gets you in comparison to solvers that are tailored to doing these problems, I don't see this in the very near future, at least.
You're looking for problems where you can get the eigenvector space.
Yes, so these, where do we have it prominently? Last line, X transpose WX for a matrix X and a binary vector, for a matrix W and a binary vector X. These are the problems that we need to formulate every computer vision problem into this way in order to run it on the annealer.
All right. Let's thank the speaker once again.
Thanks.
Thanks a lot.
Okay, so I'll stop sharing. All right.
Perfect. Thank you a lot for